Now, a very important concept in oscillations or waves is phase and phase difference. We have used these words when we were talking of interference of light, diffraction, and those times. So, today I will focus more on what this phase is and how do we write it in mathematical form. So, we have a pendulum here, and this pendulum you can oscillate. So, let me just oscillate it. Now, this oscillation can be described by some theta as a function of time, and each instant it is in some particular phase of oscillations. What do I mean? It is here at the extreme, this is a phase, velocity is 0. It is at the middle, going towards left, for me it is left. So, going towards left, this is a phase, staying here and going towards left. It is here, going towards left with some velocity at some theta, this is a phase. So, a phase means during this oscillation, what is its position, what is its velocity, which direction it is moving, and since it is a periodic motion, so the phases will repeat. So, this is phase qualitatively. It tells me in what kind of situation, state this is during the oscillation. If you write the equation for displacement, let us write for theta, can call it theta equal to theta naught, which is the amplitude, and some, let us say, cos omega t. You can write sin omega t, you can write cos omega t plus some angle phi which is constant, does not depend on time, and so on. So, this kind of equation you write. Then you have to decide the positive direction of theta also. So, if I take my left, this side as positive and this side as negative. So, this is theta equal to 0 and this is theta positive increasing, then theta positive decreasing, and then theta negative maximum, and so on. So, you decide those directions also. To give a good oscillation, one should always displace it against some surface and gently release. So, this entire phase can be described mathematically just by giving the value of this omega t. And how? Let us see, let us try. Omega t is 0. Suppose omega t is 0. What does it say? It says that theta is equal to theta naught. So, let me make a table. Theta is equal to cos of 0 is 1. So, theta is equal to theta naught and it is positive. So, the pendulum is on its positive extreme, this position, theta naught. And what is the velocity here? The angular velocity, it is 0. Once it is at extreme, the angular velocity is 0. That also will come from here. If this is theta, the angular velocity you can write d theta dt, and that will be minus theta naught omega and sine omega t. So, that angular velocity if you write, that will be, if this is 0, sine 0 is 0, so this is 0, correct. Once it is at extreme position, the velocity should be 0. So, just by giving that value of omega t, which is 0 here, you get the position, you get the velocity, so the phase is decided. Similarly, you can go for other values of omega t. Suppose it is pi by 2, what happens? Cos of pi by 2 will be 0 and sine of pi by 2 will be 1. So, it is minus theta naught omega. Theta equal to 0 means it is during the oscillation, it has come to the middle point, to the equilibrium position. It is going in which direction? It can go towards left, it can go towards right. So that also comes from here. It is minus theta naught omega. So it is going in negative direction. So it is going in this direction. During the oscillation, it is passing through the middle point, going towards this negative direction. So similarly, all values you can work out, whatever value you can give, you want to give pi, 3 pi by 2, whatever, 2 pi, pi by 3, 5 pi by 6, whatever value of omega t you give, you will get the position and you will get the angular velocity. So the phase is defined from there. If there are two oscillations, then you can also talk of phase difference. So we will put one more pendulum here and see what is the phase difference, what the phase difference is. So now I have put two pendulums from this rod. I have tried to make the length same, so that the frequency, the time period of these two pendulums remain same. This one is our front pendulum and this one is our rear pendulum. Now let me start them in some fashion. So now you see the two pendulums are oscillating, and they are oscillating in such a way that both are going towards left together, both are coming towards right together, and so on. So when the first one is at its left extreme, at that instant the second one is also at its left extreme, and so on. So if you write the equation of this front pendulum as theta equal to theta naught cos omega t, the equation for the second pendulum, this rear pendulum, will also be given by this same equation. If the amplitudes are different, then this theta naught will be different for the two cases, but this omega t remains the same. When omega t is 0, for both the pendulum, theta is theta naught, they are their positive extreme position, the angular velocity is 0, and so on. So we say that for the first pendulum, theta 1 is equal to theta naught and cos omega t, and for the second pendulum theta 2, this is theta naught and also cos omega t. So this phase and this phase, they are same, phase difference is 0. If the amplitudes are different, this will be theta 01, theta 02, different amplitudes possible, but still they will be in phase, they will be called in phase if they are going together and coming back together. Now let me start the motion in a different way. You can see the motion now. The front pendulum is oscillating, the rear pendulum is oscillating. The instant this front pendulum is at its left extreme, at that instant this rear pendulum is at its right extreme. So these two motions cannot be described by a single equation. So if I still say that my first pendulum, the front pendulum, is given by some amplitude cos omega t, and with the same t equal to 0, the same theta equal to 0, if I want to describe the rear pendulum, this pendulum, what happens? What happens? At t equal to 0, the first pendulum is at its positive extreme, at its left extreme. At that instant, this second pendulum must be at the right extreme. So that means for the second pendulum, my equation should be theta 2 equal to some amplitude and then negative of this, when this is at left extreme, this is at right extreme, and so on. So you can write this as cos of omega t plus pi. You can check if omega t is 0, this is cos pi, which is minus 1. So, this is now minus theta 0 2. So, by putting this pi here, we are able to describe motion of both the pendulums. And even if you think of velocity, one is going left, another is going right, that also can be obtained by this pi itself. Velocity is given by this expression minus theta naught omega sine omega t. So, if you write for 1, the velocity for the first one is d theta 1 dt, that is minus theta naught 1 omega sine omega t, and for the second one it will be d theta 2 dt sine omega t plus pi. So, this also takes care of the different directions of velocities. Sine omega t plus pi is minus of sine omega t, so it is negative of that. So, one velocity is positive, another velocity is negative. When one position is positive, another position is negative. So, we call this angle itself as phase. It is describing the phase, right? The phase is in what state of oscillation it is, but this describes the phase completely. And if there are two motions, so this is the phase for the first one, this is the phase for the second one, and then we call phase difference, which here it is pi. Now, we have another experiment for you, in which there will be two objects which will be oscillating, and they will be able to interact with each other. That means they will be able to influence each other or exert force on each other. So, here is the apparatus. You have two rods, light rods, these two rods, these are actually cycle spokes, and these two are balls which are attached to these light rods, and they are suspended through these holes. And the spring that you are seeing here, which is connecting the two rods, this is essentially the interaction mechanism. So, if this length of the spring increases, the spring will exert force on this one as well as on this one. So, if this moves, the length changes, or it moves this way, the length changes. If this moves, length changes. So, motion of one ball will affect the length of the spring, and then that will affect the force on the second ball. So, that is how these balls will interact. Now, this vibrating system can be vibrated in several manners. So, one is very simple, simplest, and that I will be doing it now. So, I will oscillate it, and I will ask Anurag ji to measure the time period or time for 10 oscillations, and then we will get the time period. Ready? Okay. So, I am starting the oscillations. Start. Okay. So, what is the time?
7.9 seconds.
All right. So, the time for 10 oscillations, 7.9 seconds. Okay. Now, we can vibrate the same system in a different mode. What I will do, I will compress it a little bit from both sides and then release, and then Anurag, you measure the time period. So, be ready. Okay, how much it is?
5.2 seconds.
5.2 seconds. So, this 10 oscillations is 5.2 seconds. So, you have two different natural frequencies of the same system. So, when more than one objects one particle, one vibrating system connected to each other, interacts with each other, can exert force on each other, you can have more than one natural frequencies, more than one time periods, depending on how you oscillate it, how you vibrate it. Now, the one which I did earlier, this is typically known as symmetric mode of vibration, in which both are going in one direction together and then opposite direction, and this one in which things are going with opposite phase. I talked about phase difference. This is phase difference of pi, one is going right, one is going left. This particular mode is called antisymmetric mode of vibrations, and this whole system is known as coupled pendulum. So, these are some things on oscillations, and there is one more mode which I will be showing, and look at it, very interesting. I just stretch one, I have pulled only one ball, other is almost at its equilibrium position, and then just watch and enjoy the oscillations. Alternately, one is stopping and one is oscillating. This is a mixed mode of what we did earlier. These two are the normal frequencies or natural frequencies, two kinds of vibrations, and this is a linear superposition. It is a mixture of the two. You can mix it in various manners. This is one kind of mixing in which one stops, the other starts, other stops, the first starts. So, this motion that you saw, in which one particle stops, other starts, then other stops, the first one starts, and this goes on periodically, this motion. This is because of a phenomena which is known as beats, and that occurs when in the oscillation you have two different frequencies involved. So, I will explain this phenomena of beats by taking a simple situation in which there will be one object on which two different oscillations are given to that same object with different frequencies. So, let us suppose I have an object which is given oscillations because of some force, and that oscillation is x is equal to, let us say, a cos omega t, omega 1 t, and then there is some other force system which gives it another frequency, and that is, let us say, this is x 1 and this is x 2, which is, say, a cos omega t omega 2 t. We are keeping the amplitude same, the mathematics will be simpler. So, if that object is given both these oscillations together, this oscillation as well as this oscillation, then it will have x, which is x 1 plus x 2, which will be a cos of omega 1 t plus cos of omega 2 t, and that will be 2 times a cos omega 1 plus omega 2 by 2 t and cos omega 1 minus omega 2 by 2 t. So, whether it is omega 1 minus omega 2 or omega 2 minus omega 1 does not matter, it is cos. Now, let me rewrite this as 2a cos omega 1 minus omega 2 by 2 t, and then this factor cos omega 1 plus omega 2 by 2 t. Now, if omega 1 and omega 2 are close to each other, then this is going to be a small number and this is going to be a much bigger number. So, you can describe this as an oscillations with this as the amplitude. You can write this as some a prime, some amplitude, and then cos of omega 1 plus omega 2 over 2 and times t. This is the frequency with which it is oscillating roughly, and the amplitude itself is time dependent, and the oscillation of amplitude is given by this frequency. So, a time period will be large because this is small, this frequency is small. So, over a large time the amplitude will gradually decrease, increase, gradually change, and the whole thing is oscillating with a mean frequency of something like that. So, this is a kind of beat phenomena where you have two frequencies and they are combined, and then the amplitude is continuously changing, and if they are really close enough, then you can see that over a period of time things change with a large amplitude. So, I have a beautiful experiment to demonstrate all this phenomena of beats, where two frequencies will be given to a system and you will see how amplitude periodically changes. So, here is the apparatus. We have a hexa blade here mounted on some frame, and on this hexa blade we have fixed this filament bulb, and this bulb is connected to a power source through these wires, so that I can put on the bulb. On another hexa blade we have fixed this frame, and in this frame you can see a convex lens. So, when this bulb will be put on, light will fall from the bulb to the lens, and then it will make an image on this board. And if I oscillate this lens, the image will oscillate and the frequency will be same as the frequency of this lens. Whereas, if I oscillate this bulb, then also the image will oscillate, but this time it will have frequency of this bulb oscillations, and if I oscillate both of them together, then this image will get oscillations which will have frequency of this lens vibration as well as frequency of this bulb vibration, and then you will enjoy how the amplitude of that image oscillation changes with time. So, now you can see the image on the board. If I oscillate this lens, see the spot is oscillating, and this is oscillating with the frequency of this lens oscillation. Similarly, I can make the lens state at rest, okay, almost at rest, and oscillate the bulb. I can oscillate the bulb, and again the spot is oscillating, that image is oscillating, and this time it is oscillating with the frequency of the oscillation of the bulb. So, the spot can be given, this image can be given two kinds of frequencies. If I oscillate the bulb, it goes with the bulb frequency. If I oscillate the lens, it goes with the lens frequency. What if I oscillate both of these together? Then the image will get frequencies from the bulb oscillations as well as from the lens oscillations, and then you see the phenomena of beats. So, I am oscillating both of them, and see what happens. See what happens to the amplitude of the oscillation. It increases, goes to a maximum, and then again it almost comes to a stop. The amplitude is now time dependent, periodic, because of the two frequencies, the amplitude is varying between a maximum to a minimum which is almost 0.